The natural composition variable in thermodynamics is the mole fraction because everything depends on the number of moles of substance in a solution or a mixture. However, we're more comfortable working with composition variables such as molarity, or moles per liter, or molality if you happen to be a biochemist, which is moles per kilogram of solvent. Let's see how these various composition variables are related to one another. Typically, we limit ourselves to looking at dilute solutions where interactions between solvent and solute are minimized. In the dilute solution limit, it is also easier to convert between composition variables. So let's see how we can convert from mole fraction to molality and molarity in this dilute solution limit. If we let A be our solvent and B be our solute, then the mole fraction of the solute in solution is equal to the number of moles of the solute divided by the total number of moles, or the number of moles of solvent, plus the number of moles of solute. In our dilute solution, the number of moles of the solvent is much, much greater than the number of moles of the solute, and so we can approximate N total as approximately equal to the number of moles of solvent only. Thus, we can approximate the mole fraction for a dilute solution of solute as equal to the number of moles of solute divided by the number of moles of solvent. The molality of the solute is defined as the number of moles of solute divided by the mass, or in kilograms, of the solvent. In our expression for the mole fraction, we have the number of moles of solvent, and we want the mass of solvent in kilograms. Remember that the number of moles is related to the mass through the molar mass of the substance. However, the molar mass is in terms of grams per mole, and so we are going to need to make a conversion from grams to kilograms. So the mass of solvent is equal to the number of moles of solvent times the molar mass of the solvent. That will be in terms of grams. If I want it in terms of kilograms, I am going to need to divide that by 1,000. So the mass divided by 1,000 is equal to the number of moles times the molar mass divided by 1,000. And now I will have this in terms of kilograms. Substituting this into our expression for the molality of the solute, we have the number of moles of solute divided by the number of moles of solvent times the molar mass of the solvent divided by 1,000 to convert from grams to kilograms. Notice that the number of moles of solute divided by the number of moles of solvent is equal to our mole fraction, and so we can write that the molality of the solute is equal to 1,000 times the mole fraction divided by the molar mass of the solvent. And this gives us our conversion from mole fraction to molality. To convert from the mole fraction, which is equal to the number of moles of solute divided by the number of moles of solvent for a dilute solution, to molarity, which is equal to the number of moles of the solute divided by liters of solution, we are going to need to convert from the number of moles of the solvent to liters of solution. Since we are in the dilute solution limit, the solution is nearly all solvent, and so we can approximate the volume of the solution as simply the volume of the solvent. So we need to convert from number of moles to volume, And that's most easily done if we go first from number of moles to mass, and then from mass to volume using the density, which is equal to the mass per unit volume. Density is typically given in units of grams per milliliter, and since I want liters of solution, I'm going to have to convert from milliliters to liters. Putting this all together, we can see that the number of moles of the solvent times the molar mass of the solvent is equal to the density of the solvent times the volume of the solvent. And so the number of moles of the solvent is equal to the density of the solvent times the volume of the solvent divided by the molar mass of the solvent. Since the density is in grams per milliliter and we want the volume in liters, we're going to have to multiply by 1,000 to get this in the right units. Plugging this into our expression for the mole fraction, we can write that the mole fraction of the solute is equal to the number of moles of the solute divided by 1,000 times the density of the solvent times the volume of the solvent divided by the molar mass of the solvent. Rearranging this gives us that the molar mass of the solvent times the number of moles of the solute divided by 1,000 times the density of the solvent times the volume of the solvent is equal to the mole fraction of the solvent in a dilute solution. Notice that the number of moles of solute divided by the volume of solvent is the molarity, which is what we're after. And so we can write that the molar mass of the solvent divided by 1,000 times the density of the solvent times the concentration in moles per liter of the solute is equal to the mole fraction of the solute. And this gives us our conversion between mole fraction and concentration.